Thank you, everybody who's remotely, and also everybody is attending here. I'm very happy to talk to you about this topic because I think it's one of those things that changes extremely the status quo of how we are doing machine learning. And it's federated learning. You'll see why it is so special. And it's one of those things that I feel will disrupt the industry and will allow us to train models with privacy considerations. So I hope that you, at the end of this talk, would feel the same way as I do. So the talk I have basically split in different parts. First, I'm going to talk why, and then later on, I will touch a lot of different aspects that are relevant to deploying federated learning in real life systems. And that's why I talked, when I was giving the talk, thinking about the title, I thought it's an art because there's so many different things that need to be encompassed to really provide a good solution. So what is federated learning and why you should care about it? Basically, as the world we collect more and more data, we see there's a lot of different privacy concerns and regulations that arise, from GDPR in Europe to the California Consumer Privacy Act here in California. In Brazil, we have other legislation. Japan has other legislation. So throughout the world, we see more concern about collecting the data and providing the end user with some control of their information. There's also the question of liability. Every time you collect personal data, for example, you are subject to potential attackers trying to exfiltrate that data. And we can see that recently, there's a lot of bad press for companies that don't really follow the right policies or that have been attacked. So ransomware, this type of thing, it's problematic collecting data from users. The other reason for which federated learning has become very important is pragmatics. So imagine you have been collecting in your cloud for years and years companies' data. Now you try to move all the data to a central place that's going to be very expensive. And so we need a different way to take advantage of the knowledge that we have in those data sets and data lakes without moving the data, because it's frankly unpractical to do so. There's also trade secrets. With that, what I mean is, for example, we have a set of banks or entities that don't really trust each other and that they want to train a machine learning model together. So that's not really possible right now before federated learning. If you think about how we would create a machine learning model, what it requires is moving all the data to a central place. And that is problematic for all those reasons. So luckily, we see federated learning as a way to create a single machine learning model collaboratively without exchanging any of the training data. Just to give you an idea of how practical, so you see here my phone. If you have one of those at home or at your office or here in the audience, that means that you have been engaging in federated learning without even knowing it. So Google coined the term a while back, and what they started using this technology because they wanted to ensure that while you are typing in your cell phone, they could provide you the next word prediction. Now, imagine collecting all the data that would be required to train such a model. These are the private text messages of everybody here in the audience, and that's kind of not good for privacy. So they decided to create federated learning. And that in itself is one of the use cases that we see. We see other use cases in IoT environments. For example, every time you collect information about people, like I have a smart watch, then I generate a lot of different information. It could be beneficial for everybody to, for example, create a model to detect cardiac arrest or something like that. That's another use case where potentially it's not safe to transmit all the information to a single place, but it would be beneficial for all of us. Now, entering more into the use cases in the industry, we see a lot of use cases in the consortium side. So imagine there's a lot of incidents, or let's focus on financial for a second. In the financial sector, one of the big aspects is how can we actually train machine learning models to detect fraud. There can be anti-money laundering fraud, for example, or any type of other fraud. So how do we go about that if we don't have enough data in each of the banks and we need to collaborate among different banks? So do they trust each other enough to move all the data to a central place? Not really. So that's one of the places where federated learning can really help. This use case can also extend to a variety of anomaly detection and other places where a single entity cannot really predict everything about or collect all the information that's enough for good generalizable models. We have seen other use cases in the manufacturing equipment. For example, we have robots deployed in different places. Now, robots usually don't belong to the company that is using those. Those are rented. However, when we think about this, there would be benefit for everybody to have predictive maintenance of those robots so that we don't have downtime during operation. And if everybody were to collect that information and exchange, that will be problematic because of privacy considerations. Imagine the typical use case Pepsi, or example like Pepsi and Coca-Cola, just an example. Would they trust each other? Not really, right? There's this competition. So federated learning can really help us there. I also touched the healthcare in particular. There are legislations that reduce the amount of data and require to train models, so it's difficult, and the mobile applications. So how does this whole magic happen? So before we collected everything, now I'm telling you, you don't need to give me your data, it's your data, right? So the magic happens as follows. We have parties. The parties in the example of the cell phone, where each of you, for example, with your own cell phone texting, and they each have a data set, and then there's also an aggregator that we introduced to orchestrate the training process. What's the main assumption? The main assumption is that some of this data may be labeled. So for example, if we have pictures, the cute cat would be labeled with the word cat if we were to train that type of classifier. So how does it work? First, we have the aggregator send a query to each of the parties. This query is very special in that it doesn't require the entire training data. It creates a summary, or it asks for a summary of the data, of the model itself. So imagine we are training a neural network. The query would say, take this neural network to begin with, train with your own data for a while, and then send me the reply back. So this function over here that I have represented kind of simply, that would be the training, the local training. And then we go back with the reply, which is the neural network weights or gradients. And after that, we generate a few set of weights that represent the new model for everybody. Just very similar to any type of machine learning, this does not require a single round. We usually need to create multiple rounds, so this repeats a bunch of times. And the important thing here is that none of the data actually left the participants. So the text messages that you have in your cell phones don't leave your cell phones. We have those model weights transmitted to the aggregator. Another question that I get frequently is, can you train any type of other models other than neural networks? In particular, in the enterprise setting, managing data that is tabular is relevant. And the answer is yes, we can do that type of training. The difference is what type of information is requested. So for example, if we are going to train something like an XGBoost model that is very popular out there, we would need to exchange weights and gradients, gradients and Hessians, and for decision trees, counts, and so forth. So it's possible to actually generate a bunch of different models. No, so we decided to design a really good framework for everybody to use without needing to become an expert in the entire process, because it's cumbersome And this architecture that you see here, it actually has required multiple researchers around the entire IBM to put together, because it's non-trivial. The assumption that the data does never leave requires you to re-engineer a lot of the algorithms that exist for machine learning. So that's why we generated this IBM Federated Learning. It's a framework that allows any data scientist to create machine learning models without needing to learn the inner details of federated learning. So if you can already, for example, have a Keras model to solve your problem, you can bring it to our framework and we'll do the distribution. That's what we aim to do. We also support PyTorch, TensorFlow, RLib, and basically all the popular machine learning models for different people. Then another aspect of our design is that we are cognizant that different parties have different type of data, so there's a heterogeneity in the data parties. For example, in the use case of the cell phone, some of you may be bilingual, so your text messages may have some either Spanglish or some words in French and the rest of it in English. So the prediction for everybody needs to be slightly different. So we also took care of generating algorithms that can adapt that type of thing. We try to make sure that it's easy to configure and so forth. So this is the framework, basically. We have a lot of different machine learning libraries supported and a different type of machine learning models. And you can take a look either in the product as part of Cloud Pack for Data, that's also known as Watchdog Machine Learning, so that's available there. And also, if you're a researcher and you don't want to buy a product or you cannot afford to buy a product, for commercial use, we also have a framework that you can utilize. It's over here. It's basically those things that it doesn't have, for example, UI that the product has and so forth, but it can allow a lot of research and it has all the great functionality that we provide in the product. What else? So here what you see is if you were to deploy federated learning in your company, for example, what would it take? We would need to generate an aggregator to deploy an aggregator, and also here are the parties. The aggregator, the IBM Federated Learning provides a package for the aggregator that you can see here, and then you also need to install the code for the parties at each of the participants. This is a Python-based code, and then the rest of the process it's carried out by the framework itself. How it works is basically you develop a model, you compile and save it. In the case of Keras, here you see very simple CNN. If then after that we ingest a lot of the data. This is something that each of the companies or the parties would need to implement, because the way data is stored at each of the participants may vary. So some people may have their data in Excel or in SQL and so forth. So that's why the framework allows everybody to be able to load their data according to their necessities. So this needs to be written. After that, we configure the federation, and then we deploy and train. So if you think about from the machine learning perspective, if you're a data scientist, what you need to do is create this neural network code. That's kind of similar to what you do, or exactly the same to what you do in other type of centralized training. I just wanted to flash this one. That's kind of the functionality that we have. I know it's a huge list, but I just wanted to kind of provide an overview of the different types of algorithms that we have for it. Okay, so that's where we are. As you can see, we have made tremendous progress towards enabling this type of system in enterprise settings. Now, I want to move to something interesting. In particular, for those of you that know me, I really enjoy security and privacy. So one of the big questions that me and my team ask is, can we make AI safe, and can we make sure that the federated learning system that we are deploying actually is safe and secure for everybody to use? So what I showed right now so far demonstrates that you don't need to exchange any of your data. So for some use cases, that's perfectly okay. If you can get away with just not sharing data and that's enough for you from the security and privacy consideration, that's great. But there are other highly regulated environments or other places where that may not be enough. So in the rest of the talk, I will talk about a bunch of different things that we have been studied to try to understand how safe and private federated learning is, as well as design some security measures to ensure it can be applied into different cases. So the first threat that we are going to discuss is inference of private data. This slide that I have here pertains to any type of machine learning model that you have, regardless of how you train it. So what you see here is a model that's trained, and it was trained using a bunch of different pictures. From the privacy consideration, some people argue that it's actually very bad if somebody can get that model and start querying it and deciding whether a particular sample or photo was used for training that model. So just that show hands in the audience, how many of you think that's problematic? Okay, I see good show up, okay. So around like less than half, or the rest of the people seem to think that this is not a real issue. So let me give you an example where this may be a situation that we want to consider. Imagine that this model is trained from the pictures of people that belongs to a particular political affiliation, or people that has a particular disease that it's taboo and they don't want to reveal. So if that's kind of example of real life in the company setting, imagine that these are documents. And if you could determine that a particular document was part of the training set, you would be able to exfiltrate the information that was used. And that's an interesting threat model. So the way these attacks happen is, you see this little guy over here, that's my attacker. That attacker would start querying the model and generating enough in a very particular way until he knows Bob was part of the data set. Again, if he had this disease that he didn't want to share, that it's a privacy violation. It happens for every type of model. Now, let's consider the particular use case of federated learning and what is the new attack surface that we are examining. Here, the party sends back to the aggregator replies. These replies were those neural network weights, right, that I was showing. So how many of you would say that that's problematic and that we could use that to attack the system? Maybe show hands. I see Farhan. Okay, the rest of you don't think. Let me show you. There's this attack in the first column that you see, and it's not loading. Okay, the first column, what it's showing is the model updates. If you were to kind of demonstrate and plot them in a picture. And there's an attack that is capable of generating the samples that are used. This attack has like some caveats, so don't take it at heart. I think more and more people are getting more advanced attacks. But what it demonstrates is that there is some risk of re-identification of training samples by inspecting these replies from the participants. So because we have a lot of different companies that need to be aware of the risk of re-identification and extracting of data, there's also a lot of new techniques that have arisen to protect the federated learning process. Most of them, as you can see in the list over here, are cryptographic techniques that enhance the security and privacy of the system. So I will tell you a little bit about that. One of the aspects that has been propose is basically, rather than just sending the neural network weights that you got for your neural network, now you add some differential private noise. What that is basically some noise that the way I like to colloquially say, it's kind of providing you deniability, plausible deniability of what data you hold. That's basically a way to see it. The problem with local differential privacy is that it messes up your accuracy of the model. And why are we training machine learning models? To predict. And if you cannot produce something that it's valuable, then who cares, right? So we created a new approach that is based on a combination of multivariate computation and differential privacy. So for those people in the audience that are not very familiar with multivariate computation, I have here an example. What you see there are two participants. They engage in the federated learning process. They generate the model updates. Those would be the neural network weights. And after that, they would encrypt the model update using a multivariate computation technique. This is slightly different than the traditional public key, like some other crypto systems. So let me tell you why that's the case. So what happens in this type of multivariate computation crypto systems is that the model update that's encrypted gets sent to the aggregator. And the aggregator is able to use that encrypted data and still generate a new model. So it basically adds this one and this one without decrypting them. So the way what we get at the end of the day can be two different things. The option number one that I have there in the slide is the aggregator can generate the new model for everybody, and it can generate it in plain text. This is useful, for example, if you want to deploy, the aggregator wants to deploy the final model. In the case of the cell phone that I explained before, they do want to have the model in plain text for that reason, because they want to use the model at the end of the day. But for other use cases, in particular for those where regulation is very specific about what data can be transmitted and what knowledge can be extracted, we have other crypto systems like fully homomorphic and Palier that would allow you to have at the end of the day the model encrypted at the aggregator side, and only the participants can decrypt that model. So as you can see, you can select from all these different crypto systems depending on what is it that you want at the end of the day. So I told you that we were going to improve the local differential privacy. By the way, I have added at the end of the slide the references of the paper where we have all these different approaches detailed technically. So the way we're going to combine differential privacy and multivariate computation is basically the following. Differential privacy is a very mathematical approach, so we can demonstrate that if we inject only a proportion of that noise, we can still provide the same privacy guarantee, and that's what we are doing. It turned out that this is what I like to call a match made in heaven, because we were able to have very good privacy guarantees without adding too much noise. So why should you care? You should care because if you were to use differential privacy, you would see this line over here. In the Y value, you see the F1 score that basically measures the quality of your model. If you were to deploy this, it really provides very bad quality in some sense. But if you deploy our solution, we can see that the F1 score actually maintains across the different experiments that we run. All right, so the next question that you want to answer is if you really want to make sure that your system is secure and you want to deploy it, well, what type of crypto system should you use? Can we reduce the training time? Because crypto is not for free. It does require some extra overhead. So that's another aspect. What if parties leave and join? In the case of IoT devices, that is a situation. So if they leave, we want a crypto system that does not need requeuing constantly. So this is basically the first approach where we have threshold palier and partial homomorphic encryption. And there, the idea is that you don't trust the aggregator. I think I covered this slightly, but just to demonstrate and give a sense of what's happening behind the hood. What's happening here is that the aggregator is the one untrusted, and the parties get to obtain their private key. So they would train in plaintext. After that, they extract the model updates, they encrypt their model updates, and send back those encrypted model updates to the aggregator. The aggregator takes all the encryption and computes the new model. Again, the result gets to be in ciphertext. And this basically repeats until we find the right model. There are other types of crypto systems. So imagine that you have a use case where different parties don't trust each other necessarily, and they would say something like, we are not decrypting anything unless 5 parties are participating. So why do we want this type of crypto system? It's for collusion purposes. So imagine that 2 companies decide to collude to get information from another one that would be restricted if we were to select this type of threshold of crypto system. The last one, this is a new crypto system recently with respect to the rest of them. It's something that we proposed that uses functional encryption. This is a type of encryption that is quite straightforward to implement, to use, because it does not require that many rounds of communication. So as you can see in my chart, just like for awareness, these different crypto systems all come with different cost in communication, as you can see, with threshold palier being the one that has more communication rounds, and this one being the one that has the least. So that's something important also when we are deciding what type of crypto system to use. All right. I also wanted to mention something that we recently studied. And when we were starting, basically, everybody was thinking, okay, if you encrypt, that's enough privacy, everybody's happy. But as everybody in the security field knows, this is only an invitation for people to try to see what's wrong with it. So there's a disaggregation attack that was reported. The idea here is that, as you may have remembered from my chart, the animation, I said, like, we need actually multiple rounds to train a single machine learning model. So this over here is what's called a participation matrix, and I'll show you how it's built. Imagine that in round 1, everybody sends their encrypted model updates. In round 2, only those 2 participants send their model updates. And in round M, we have a different set of participants. So what this attack does is that it uses that participation matrix, and it builds a system of equations to try to isolate certain participants' model replies. And it's encrypted and everything, but it's possible to make sure that to have this attack work. So we created, to fix this situation, what we call T-Trust. And the idea is to provide transparency of the entire training process by ensuring that the situation where a participation matrix can be used to build system of equations cannot occur whatsoever. So it uses a type of crypto system, and we basically deploy the keys at each of the participants to ensure that each round can only be decrypted by the aggregator if everybody needs to participate. Who needs to participate is participating indeed. All right, so the second threat model that I want to show is manipulation attacks. So these are slightly different in that we are no longer trying to infer information. Now, a participant in the training process is trying to modify the machine learning model to their advantage. So what does that mean? One of the attacks that that's very popular is called a backdoor attack. So think about a backdoor in real life. A backdoor is something that it's probably behind the building. You don't see it necessarily, and potentially very few people know about it. Same here in machine learning. These attacks, by the way, exist both in federated learning and also in standard machine learning, even if you transmit out your data. So imagine you have an autonomous driving system, and the adversary wants to make sure that your system does not work very well in certain situations. In this example, what the adversary wants to do to your system is that every time it sees that stop sign and it sees that post-it note in the middle of it, it wants to make sure that it's classified as a speed limit. That's problematic, right? If you imagine you are driving your car, self-driving car, and then all of a sudden you don't stop at a stop sign. It's pretty bad, right? So how does it work? It basically, the adversary manipulates the training process by adding samples that generate this. So he or she would add this stop sign, the post-it here, and then he or she would relabel the data to speed limit. With that, the machine learning model, what it learns is that, oh, every time there's a stop sign with that little sticker, I need to misclassify it as, or need to classify it as speed limit. Now, that's one of the aspects. The other type of threat model that we consider is Byzantine attacks. So here, imagine some of the participants decide to send something bogus to the model. I phrase it here as an attack, but it's possible that some of the systems, for example, when you have IoT devices, you can have some of those devices failing for really honest, normal device reasons, right? So in those cases, we need to make sure that if we are ingesting data from devices, we are robust against those failures that are natural or malicious, both of them. So from the defender perspective, let's think about the defense. I love defending stuff. So I'm always not only thinking about the attack, but also what can we actually do about it. From the perspective of the defender, it's difficult because remember that now we don't have even access to the training data. So how do we know if there was a stop sign with a post-it note? We don't know, right? Because it was hosted by this guy. So that's a problem. What happens if we actually have, for example, if these are sensors, if we have two sensors that are generating data that is malicious or bogus? We don't know that, right? What if the aggregator is malicious? That's another potential thing that we need to think about. So in reality, in most of the cases, people assume that the aggregator is the one that's the defender. Why that's the case? Imagine we have a federated learning provider, and that provider is really interested in making sure that it can keep selling their federated learning stuff. So it's usually the aggregator that's assumed to be the defender. And there's also other stuff. So sometimes, for example, in the use case of the cell phones, it may be that each of you has different types of text messages. Just being different doesn't mean being malicious, right? So that's what it's called non-IIDness or heterogeneity of the data. So detecting we cannot just drop anybody because they are different. It may be actually valuable information that we would need to kind of bootstrap as opposed to just remove. So that's one of the issues that we have from the defender, or the challenges. There's also different participants with different data points, and the quality of data is unknown. So that's the challenge. We have been working actually in developing defenses for these type of threats. What you see here is one of our approaches. We call it legato. For those of you that play music, this may ring a bell. The idea is that we have to mitigate or to reduce certain model updates, but not drop them. So if you look at the spectrum of solutions out there to mitigate this type of attacks, what they do is they say, oh, let's see who looks like an outlier. Those three look like an outlier, just remove them. we are trying to do something slightly different so that if it happens that it was not an outlier but valuable information, we can still have that into the model without risking the model drifting the decision boundary drastically. So that's one of the parts. And I also would like to mention something that I find really interesting and a dichotomy here is that at the beginning in the privacy, if you remember, the one that was not trusted was the aggregator, right? You're trying to hide everything from the aggregator. We don't want to show the model updates in plain text and whatnot. But here, in the other hand, we have the aggregator playing the defender, and that's a problem. So that's something that we are trying to actively make sure that we can both hide some information from the aggregator and at the same time provide protection against manipulation attacks. The title of the talk was The Art of Creating Federated Learning. HPO, and I forgot to spell it, but that is hyperparameter tuning. So for those of you, let me show hands. How many of you are data scientists, have trained models? How much of your time do you spend in hyperparameter tuning, like roughly? I love that. I love that. So he just said that auto AI solves the problem, but there's the need for auto AI at some point. So in federated learning, the hyperparameters also don't adjust themselves. They are something that need to be played with, and it's a problem that's slightly different. Cannot just plug the auto ML systems that exist out there because not all the data is in the same place again, right? So we have been working also, there's this paper that we have where we propose solutions to try to enable people to use it without fine-tuning all the hyperparameters that happen to occur here. For example, we have the fusion algorithm. This is what aggregates the models. There's some hyperparameters there. There's also hyperparameters at the parties. So you need to use different hyperparameters at each party. And that's what we're trying to solve in this problem. It's an art, and we are making sure that it's easy to use. The other aspect in real life is bias, machine learning bias. And this is, I think it's a problem that everybody should care about. What do I mean by bias? And I'll let you read a little bit this. So more and more machine learning models have been reported to be biased against certain subpopulations. And that ideally should not happen, in my opinion. And I think a lot of people here would agree with that. So the question is, can we mitigate bias in federated learning? And this is another thing that we have been studying. How can we create machine learning models that do not learn that biasness from the data itself, but also are we generating more sources of bias by introducing federated learning as opposed to centralized machine learning? So that's something that we work on. As you can see there are a bunch of new sources of bias that need to be mitigated. We have this paper where we propose a bunch of solutions also. So it's a relevant problem, and we want to tackle that one as well. I kind of also wanted to show something about accountability, because in the government sector in Europe, this is something very important. And this is a project that we run with a German collaborator. The idea here is that imagine you have, well, they do have regulation that requires them to verify how the process took place, so that in case there's something that doesn't go appropriately, they can be audited. So here we have things like, did everybody follow the right procedure? Did they add a differential privacy? Did anyone injected something bogus? That's sort of the questions that we want to answer there. And to make sure that we can actually be audited, it turns out that we need to log a lot of information from the different process in the system. So starting from the project specification, the pre-processing of the data, things like federated learning process, how it went, and so forth, so that later on we can have the auditor verify this. We have a lot of resources out there. At the end of the day, what we generate is a fact sheet. The fact sheet provides the auditor a view of what things happen, and whether there were certain aspects that were needed or not followed in this process. So imagine, for example, that we really wanted to generate a machine learning model that was fair. So we could inject, as part of the verification process, one flag that says, was this fairness fusion algorithm utilized for the creation? And if not, the auditor can see very fast, oh, it is not the case. So that means you need to reproduce the model and you cannot publish it, for example. So you can start automating this type of thing. Let me see, how am I doing on time? So other things that we want to verify is, for those of you that said we're machine learning experts and data scientists, you know that we oftentimes don't get the final machine learning model, the model of your dreams in the first try. And it's the same in federated learning. So you need to keep track and have a provenance-based solution so that you know what experiment led to the actual model and what hyperparameters. Also, the reproducibility is really important here. So that's something that we are looking into. The other aspect is, this one is in particular relevant for GDPR, is the right to be forgotten. So as part of the right to be forgotten, one of the things that we need is to ensure that, for example, let me pick on Farhan over here. Imagine Farhan says like, no way, I'm not providing my data anymore for your model. Then the company has two options. Either they start training a new model from scratch, or ideally they can take the same model and remove that data without affecting the rest of the users that much, or rerunning the entire learning process. So that's something that we also have been working. I have added the reference there. And to kind of end the talk, I would also like to mention something that is an interesting case, and it's the vertical federated learning. It's slightly different. The idea is the following. So what I have been talking so far, it's the horizontal use case. In this example, you see hospitals. All the hospitals are generating the same type of data. That means those x-rays that I have put there. And they would label their data accordingly, but it's the same data, right? X-rays are x-rays. In vertical federated learning, we have a different use case where each of the hospitals actually is collecting different data. So think about your primary physician, then you also go to a different hospital for lab records, and then another hospitals for the x-ray and the actual diagnosis. When I created this slide, I was thinking about COVID, so that's why the diagnosis had that x-ray with the COVID result. So if we combine the information that's different from all of the parties, then we generate that feature vector. That's really a good use case, an interesting use case, and it extends a variety of other places. For example, in the financial sector, we have real use cases where different banks and the regulator may want to collaborate, and each of them are collecting, by definition, different type of data. In this example that I have here in the bottom, also you can think about the supply chain. So the first part, a product gets produced in a factory, then we collect some information about that production process, then it gets transported to a central place, for example, in a container, and we can collect more information about that using sensors, for example, temperature and so forth. And then it arrives to the distributor that finally sells or not sells the item. The distributor knows how long it was in the shelves. It also knows whether the item was returned, whether it was damaged, so the label is with the distributor. So these type of use cases, unless you use a system where you move all the data to a central place and try to convince all these entities to move all their data to a central place, that's going to be very difficult, right? So Vertical solves that problem by using cryptographic techniques to keep the data in the same place while still allowing you to generate a model. So there are a bunch of different techniques when we started this. Some of them did require peer-to-peer connectivity. We came up with something quite different where we remove all the peer-to-peer communication by introducing functional encryption. And as you can see there, we actually were able to reduce drastically the amount of time that it takes to train a single machine learning model. All right, so I have touched a lot of different things today. I tried to provide kind of an overview about the art of creating a federated learning system that encompasses so many different aspects: accountability, robustness, privacy, and so forth. There's a lot of things that you can think about also from the machine learning perspective. And we have a book that we recently published on these topics. So what I tried to do today was to provide an overview, but if you really want to go to the substance of it, I invite you all to take a look at that one. We have had chapters contributed from top researchers around the world, including MIT and so forth, as well as all the research that has happened here at IBM. So I really invite you to look at that. And so this is me. Thank you very much. And yeah, I'm open for questions.
One question.
Okay.
Just a quick question.
Yes.
Oh, just a quick question in terms of how performance is impacted when you're learning, deciding what kind of model and converting over to a kind of a federated model. How much is performance a consideration?
So performance in what sense? The machine learning performance?
Yes, someone taking an application using these models.
Okay. So if you generate imagine I'm going to answer the question like by explaining what I understood first. So if you were to have all the data in the central place versus having the machine learning model running distributed federated learning, it depends on the data. Sometimes if the data is non-IID, you would need to use robustness algorithms to make sure that your model is exactly the same. Most of the time, because you get knowledge of more parties, you would actually generate better models. With respect to the actual generation of the model, I'm not sure if you were referring to this slide, so let me go back.
Or you have the different going back and forth.
Oh, okay.
No, I would actually, you answered my question already, but
So in this whole process, we do have this back and forth, right?
Mhm.
Yes. So this back and forth happens multiple times. How slow or fast, it depends on the connectivity among the parties. One thing that's really interesting about federated learning is that if, for example, the data that you have in all of the parties is huge, this is quite inexpensive with respect to that, because the data doesn't move and the neural network in itself is not that big. So the amount of data that you transmit, even though there's multiple back and forths, it's not that much in comparison. So it depends on that. It's actually used by things like NASA, in use cases like NASA, because they have to transmit a lot of data and it's far. So they prefer doing federated learning as opposed to transmit the data itself. Yeah.
Debbie, were there other?
Yeah, there were so many great feedbacks from
Okay.
the audience. Thank you so much. So first, we take questions if there is from audience here, and then we can see from the WebEx. So is there any question in the room? Yeah.
So in this setting, like, do all the parties seem there can be like little variations of the inputs.
And can you please repeat the question?
Yes, I'll repeat the question for everybody. So the question was, do they need to agree on a single machine learning model before they start training, or can, for example, party one bring their own CNN and the other one have a BGG? Is that the question? Okay. So the answer is traditionally they all need to have the same model. So that when they aggregate, the matrices match nicely. There are some approaches where you can have different machine learning models at each of the parties, but then integrate them becomes a little bit trickier. If you see here, I have added this function, and it's a subtlety. That function would be slightly different if you had different models, but it is possible. Yes, there's research on that, but when you tell somebody about federated learning, they assume everybody has the same model. Yeah. Mm-hmm. Yes. Yes. So the question was, can any machine learning model be federated? We have federated different models. It does require some engineering and thinking. So, for example, XGBoost, we created our own algorithm for that one. We can train logistic regression, SVM, K-means. There's also reinforcement learning in our library. So it is possible to do that. It did require, although for people using the library, they still, for example, if they are training something like a reinforcement learning problem, they still use RLib as normal. But behind the scenes, we did a lot of changes to make sure that the data was not transmitted. So yeah, we can do that. Yes, it is. So the question was, can we go ahead and use it? Yes, if you go to this website, there is, yeah, I should have added the link with the take a picture situation. But also if you Google IBM Federated Learning, you can basically either use it as part of Cloud Pak for Data, where Cloud Pak for Data is only installed at the aggregator side. You don't need to install Cloud Pak for Data at the parties. Or there's also as a service where basically IBM hosts the aggregator and you can connect there through cloud. So we have those two options and they are running. Mm-hmm. There's another question.
In comparison to Google or Facebook, how do we compete? Like compete federated learning, and what are the competitors, commercial and open source?
Great question. So the question is, are there any other frameworks and how are we doing with the competition? So there are other frameworks out there. NVIDIA has a framework. There's a bunch. I think last time I checked, there are 15 different frameworks. What makes our framework unique is as you can see here, we don't get married to a single type of library. So we support PyTorch and TensorFlow. So if you happen to love PyTorch, you don't need to learn TensorFlow as other libraries do. And then also we were very conscious about ensuring that the security and the entire pipeline was covered for companies. So we don't need to open ports, for example. We don't require peer-to-peer communication among participants and so forth. So we were very cognizant about those details that are important for the enterprise settings. The other big difference is that, again, you like here, let me see. Here, for those of you that are familiar with Keras, you don't need to learn anything else. You already know what you need to know because you're a data scientist, so you write your neural network the way you like. And that's another differentiator that we have.
It's almost like in place.
And open source. So,
One day. Yeah. Yes, I'm sure.
yes. So the question is, what happens if, for example, we have a pre-trained neural network and we want to try to fine-tune it with federated learning? It is possible. So what you would do is basically you load that neural network, and we start from there, that point onwards, to train and learn the model with the new data. Sure.
Great, thank you so much. So there are a lot of other positive feedbacks coming in. Thank you. So there are some questions. One question is, are some of the supported federated learning models less prone to the inferential attack than others?
Okay, so the question is, are some types of
Are some of the supported federated learning models
less prone to inference attack than others? That's an interesting question. So, for example, what happens if we are training an XGBoost model versus a neural network? Do we have different attack surface for those? They all suffer from that. Frankly, every time you have a machine learning model out there, there's inference that you can provide. So the thread works for a bunch of different models, yes.
Okay, thank you. And the other question that was asked is privacy and adversarial robust?
I can
Yeah,
read.
sure, thank you.
Hello, Natalie. Thank you for the talk. Is privacy, adversarial robustness together and robustness feasible in federated learning setting and from a model utility perspective? Because both TP and adversarial training reduce model accuracy. Would the accuracy be low, too low? Okay, so just for everybody in the audience, what this question is about is when you have some attacks that are called adversarial samples, what the adversary does is basically adds some noise to the image, and it gets misclassified for that reason. So there's a technique called adversarial training, and that makes your model more robust against those perturbations, but it also, surprise, surprise, reduces the accuracy of the model. So the question is, if we are in federated learning, are there any ways to actually mitigate that problem? There is some work on creating robust models under federated learning. It is possible. And can it be combined with DP? It can be combined with DP. In fact, sometimes, for example, when you have some techniques for robustness do allow for differential privacy and for adding noise, Gaussian noise. So it is possible to combine. The accuracy is going to be hit for sure. And new approaches are I think, in order for those types of problems. So, yes.
I think that's it for the questions.
Okay.
Okay, I think that's it for the questions. Thank you so much, Natalie. So I just want to thank you again for coming, and we heard a lot about machine learning, and understanding all the use cases was very useful, and I think it's going to want us to learn more and go out and try these things. So thank you very much. And also I wanted to mention, and I also want to thank Seppi for organizing these events. She's organizing all our affiliate technical talks, so with these marvelous speakers, so thank you so much. We have another one coming up in October, I believe on cybersecurity, perhaps. And I also want to mention that today is the beginning of Hispanic Heritage Month, so where we celebrate the culture and the accomplishments of the Hispanics and Latinos in the United States and worldwide. And also within IBM, we have many, many events. And on behalf of the Familia at IBM Bay Area, which is our Hispanic Latino BRGs within the United States, we are hosting now a little fiesta for the folks here at Almaden. So sorry for those people that are virtual, but we'll have some music and some goodies and play some games with cool swag. So in any case, thank you so much for those that also joined us virtually. So, and stay tuned for our next Tech Talk next month. Thank you so much. Okay, thank you.